Imagine a single star outshining an entire galaxy. For days, one point of light floods space with more energy than our sun will produce in its entire lifetime. That is a supernova, nature's most spectacular way to end a star's story and seed new ones. Iron, calcium, the oxygen in your next breath, forged in stellar cores, scattered by explosions like these. So when we say powerful, we mean galaxy-scale powerful. But power isn't the mystery. On April 11th, something happened in deep space that shouldn't exist. Welcome to WTFACT AI Official. Today we investigate why our best simulation said this explosion should fail. Atlas is 4 robotic telescopes, Haleakala and Mauna Loa in Hawaii, plus twin stations in Chile and South Africa. Every clear night they sweep the sky in tiles, again and again, mapping how brightness changes. A computer subtracts tonight's image from last week's, difference imaging that makes the new stand out. If a pixel brightens or vanishes, the system raises a silent alarm. Most alerts are noise, cosmic rays, satellites, image smears. A classifier culls the fakes, ranks the real, and pings astronomers before dawn. At 3:21 a.m., a new point flared inside NGC 3621, where there was only darkness hours before. Within 6 hours, observatories worldwide re-aimed. Why the rush? Early fingerprints vanish in a day. Spectrographs split the light, revealing temperature, elements, and velocity. The profile screamed core collapse supernova, but the shape hinted at something cleaner, more symmetrical than models allow. So teams booked the Very Large Telescope. The clock was ticking, its instruments locked on, slitting the light for deeper spectra. What did the spectra reveal? A serious problem. The data didn't match the theory. Massive stars live fast. Hydrogen, then helium, carbon, neon, oxygen, silicon, layered like an onion. Deep inside, silicon makes iron, but iron is a dead end. Fusing it costs energy. As the iron core nears about 1.4 solar masses, the Chandrasekhar limit, electron pressure fails. Gravity wins. The core implodes in 1/10 of a second. Heat soars. Photons smash heavy nuclei, photodisintegration, draining energy from the shock. Electrons are slammed into protons. Neutrinos flood out by the octillion, carrying energy away. The inner core stiffens at nuclear density and rebounds, core bounce. A shock wave surges outward, but it stalls within milliseconds, choked by infalling matter and lost energy. Without a revival, collapse continues. The star disappears into a black hole. That's the default our textbooks teach. Yet SN2T24GGI did not fade into silence. It exploded, and did so cleanly. Observations show near-perfect, symmetric expansion, not the messy, unstable outcome our models predict. So, what revived the shock? Neutrino heating? Magnetorotational jets? Something else? Whatever it is, our best 3D simulations say it shouldn't happen. And yet, it did. Brightly. The universe played by rules our code didn't capture. A hidden mechanism, still invisible to our equations? Or missing physics in turbulence, microphysics, or neutrino transport? Until we find it, collapse to black hole remains the safe bet, except when reality disagrees. SN2024GI is the disagreement. So why did this one explode, and perfectly? To test ideas, scientists build stars inside supercomputers. They solve fluid equations on adaptive meshes, tracking gravity, magnetic fields, and, most painfully, neutrinos. In 2 dimensions, a little neutrino heating behind the stalled shock can be enough. The model explodes. But in full 3D, turbulence drains energy differently. Hot bubbles cool, flows tangle, and the shock fizzles. The neutrino-driven fix underpowers the blast by roughly an order of magnitude. So what about jets? Spin a magnetized core fast enough, thread it with fields. Narrow beams could tear a star apart. In clean 2D, jets punch through. In realistic 3D, they wander, kink, and die unless rotation is extreme. Caltech researchers asked a sharper question. What if the star wobbles by only 1%? In nature, nothing is perfectly steady. What happens if the star isn't perfectly steady? Add a tiny asymmetry, a 1% wobble in rotation. At first, jets form, thin, bright, confident. Then the kink instability grips them, like a pressurized hose slipping free. The jets precess, twist, and whip. Energy that should drill a path outward smears across the core. Instead of a focused engine, turbulence blooms. The shock weakens. The explosion stalls. Collapse resumes. In the simulation, the garden hose effect kills the blast. Yet the real supernova did explode, and its shell looked nearly spherical. Either nature stabilized what our code could not, or we're missing physics. What pieces are not yet on the board? Maybe neutrinos reshuffled heat, or stiffer cores, reconnection, rotation. Even dark matter or axions. Test it when Atlas pings. Artificial intelligence learns patterns from the past. But the universe is not a data set. It is a performer. We watch only from one seat. Our simulations are maps, not terrain. They compress infinity into rules we can compute. SN 2024 GGI reminds us that nature keeps side doors we haven't found. That is not failure. It is direction. Build better instruments. Share alerts faster. Simulate with fewer assumptions and finer physics. And keep a margin for wonder, because every time the sky breaks our code, it writes us a better one. Subscribe to WTFACT AI Official. The deeper we look, the stranger and clearer the universe becomes.